I know. I'll lean in a little bit more then. All right. So I'm going to be talking about ring-1, ring-2, or essentially, like, you can't hear me? All right. I'm going to be talking about ring-1 versus ring-2. Ring-2 is a colloquial term. We'll get into that in a sec. Pete Markowsky, some of you may know me, some of you don't. I'm a senior security researcher at Crucial, which was bought up by the Harris Corporation last April. Before that, I used to work on like SBIR research related to like hypervisors and other stuff. So, what are we going to talk about? System management mode, system mode interrupts, system management mode interrupts, virtualization on the AMD platform, and the interplay between the two. Like, essentially, when you can get execution, which one runs, when it does, and which one can supersede the other. Why should we really care? Well, like I told you a few seconds ago, when I was working on SBIR research, we were trying to build a hypervisor that was essentially designed to isolate a process from a malicious system. The goal was, even if the attacker had root, that they shouldn't be able to get at the executable on disk because it'll be encrypted. A symmetric key would be stored inside the hypervisor. You would use that hypervisor and like page table trickery, thus to hide the executing copy of the code from the rest of the system, so that only the hypervisor and only the stuff with the key would be able to get to it. The thing about this is, normally system management mode, like that code runs outside of the protections of VMMs on AMD-V. If you look in the manual, like it's highlighted where it says, oh, by the way, you can just you let system mode interrupts be taken normally, and this will run outside of your VMM. So for someone like myself who's afraid of possibly having like code that could be injected into a system management mode, and then you could use that code to read things like keys, that becomes a big problem. So our assumptions are that the attacker has the ability to install an SMI handler. They could take advantage of like BIOS overwrites or cache attacks. Like some people have probably seen like the Weak to Floats, and I'm maybe butchering his name, so please like let me know if I am. Basically, the problem is like we assume they can install the handler. They could have like root or system privileges in the guest where they can load drivers and everything else. And they may have even subverted the BIOS up to a point. So where they can actually install the handler by having their own like crafted BIOS. You could take something like Core Boot, which used to be Linux BIOS, roll your own system handler in there, throw it back up, and there you go. And now you have something running in system management mode. So again, to sort of restate the problem graphically, because it's always better, you'll notice that I definitely can't do art. That's why I'm doing this. Essentially, what you have is you have in the upper corner over here on the left, you have a virtual machine monitor. It's running, and it's executing, and it's putting guests over here. The problem is the system mode interrupt happens. It goes over, like execution gets transferred to the SMRAM, which is where the SMM code lives, rather. And to put it bluntly, this happens, and it has full access to RAM. So this is the problem. So what is it? System management mode is essentially a 16-bit operating mode similar to real mode on x86. It's supposed to be transparent to the OS. What that means is that when it gets invoked, execution stops, state is saved, execution is transferred over to the code that runs in system management mode. It happens, and then it's supposed to resume such that the instruction then can begin running again, or where the operating system was when the system mode, management mode got changed into, can be resumed immediately, as if nothing had happened. It's supposed to be entirely invisible to the OS. The OS doesn't know about it. The OS can't find it, shouldn't see it. Originally, this was designed for power management and other stuff, and introduced with the 386. So it's been around for quite a while. You only get into system management mode when there's a system mode interrupt. And a system mode interrupt is only asserted by hardware. Again, like I said, this is called ring-2 because really there's normally no restrictions to the I/O or the memory. It's ring 0 code starting out in 16 bits. And it basically has access to all of system memory. And you can... There's some restrictions, not restrictions, but there's some caveats as to how you go about this. But essentially, for the sake of our talk, we have to assume that if you have code in system management mode, then you can basically touch all of system memory, not just what the BIOS gave the OS. So, like I told you earlier, system management mode lives in a place called SMRAM. It's a range of physical memory. it's defined, like you can find the start of it because there's a model-specific register called SM base. This points to the start of it. On AMD 64, the default size is 64K. Though using other registers, you can actually set that between 32K and 4 gigs. So where does this all come from? Like, your SMRAM gets configured and set up by the BIOS, or the system firmware. What happens is BIOS will set up SMRAM, essentially copying a handler into it, configure system management mode, model-specific registers, and then it'll simply lock access to those registers by setting a bit in the hardware control register called the SM lock bit. The idea is that by controlling these registers and then configuring them appropriately, you can prevent getting access to SMRAM. And the way this works is that there are 2 segments that are provided in which, there are 2 segments of physical memory that are provided such that reads or access to them is denied unless you're actually in system management mode. On AMD 64, you have the A seg, which is a legacy segment, and they have the T seg, which is defined by 2 model-specific registers. The reason for this is that way you can reposition the code later, so that if you have a BIOS that needs to use like legacy, have more compatibility with legacy operations and use like lower ranges of memory, you can actually move it to a higher range. And the SM mask MSR actually has like 2 bits in it for the A seg and the T seg that say protect this, don't protect this. When you enable those bits, you essentially can't get access to those segments unless you're in system management mode. So what is a system mode interrupt? Essentially, it's a non-maskable interrupt that takes priority over all other interrupts. There are 2 types: internal, which are generated by hardware in response to like in-out and ins-out instructions or IO-IO instructions. Which ones depend on like the logic you have in the motherboard. External ones are like generated by hardware. So you could have something that goes off like a thermal alarm or whatever. It says I need to spin up a fan. It switches modes over. And this causes you to switch into system management mode. Essentially, what this diagram says right here is this is like all the operating modes you have in AMD 64 and AMD-V. Essentially, the gist of this diagram, as complicated and as weird as it is that pretty much at any time you can switch into system management mode, provided there's a system mode interrupt. So during a system mode interrupt, what happens is the processor stops fetching instructions, waits for currently executing instructions to finish and buffered memory writes to finish so the state is clean and everything's solid. Copies all of the appropriate registers into this SMRAM save state, and then changes the instruction pointer to start execution and the SMI handler, which exists at SM base. So it exists at hex 8000 inside system management mode, or SMRAM rather. So the handler itself is really just it starts out as x86 real mode code. So 16-bit code, and it it just runs normally. It could set up long mode, it could set up protected modes. You can actually get access to more stuff, set up paging, set up software interrupts. And then when it's done, it uses the resume instruction, the RSM, which signals that it's time to leave system management mode and return back to the previous operating mode that was invoked when the SMI was asserted. In a lot of papers, like a lot of stuff like in FRAC and other stuff, they've tried to do get more access to things and actually show off how this works and how to get access to all of memory from this. What happens is they found that address translation is somewhat difficult, and the reason for this is that you have to actually read the CR3 value from the save state area and then actually sort of walk the page tables by hand and implement your own walker to go find stuff and to go figure everything out. Oftentimes, a lot of privilege escalation attacks and other stuff that would come from this, what will happen is they'll actually overwrite values in the save state area, and then they'll invoke the resume instruction, which will then read the save state and immediately say, oh, my instruction pointer, DeFloat's original attack that he presented at CanSec West back in 06, what he did was he actually modified the save state area so that it would contain the instruction pointer of his code afterwards in ring 0. So the idea would be he would bypass everything by saying, oh, okay, when you get out of this handler, call resume, run this code over here, now it's running as privileged, it modifies data structures and goes. So again, how do we install a malicious handler? There's a few ways you can do this. Simplest in terms of like development time is in a lot of ways is just install a modified BIOS. Get something like core boot, set it up, like hack into it, and just write code to DRAM the same way the BIOS would. Is you're just writing your own handler. It just has to read keys or values from other parts of DRAM. Other things that people have done, they found like the Invisible Things Labs people, they found a bug in the SMI handler for the Q35 stuff, and were able to use that to get their code into SMI, or into SMM rather. And from there, they were able to do all sorts of stuff. And then there's the other attack that came out at CanSec West last year, which is where by manipulating x86 caching, you're actually able to say, well, this copy of SMRAM is cached, and it's mapped as write back, and so you're going to end up doing a whole bunch of writes to the value of SMRAM that even though it's not mapped because you're not in system management mode, the idea is that the L1 cache is going to be populated with your data, and then all you have to do is trigger a system mode interrupt, and then rather than fetching the data from SMRAM, you end up fetching it from the L1 cache, in which case you have this sort of disparity between what's in the cache and what's actually in SMRAM. So, like I told you before, my thing was we were building a VMM. The goal was to isolate a process from a malicious system. So we have to assume that the attacker has the ability to do pretty much whatever they want on the box, provided that our VMM can isolate them. So our goal out of this is to actually say, can we take system management mode and like isolate it and make it subject to the protections of the virtual machine monitor? The nice part is that if you look through the developer docs and everything else, this is actually part of the design. So the goal of this is what's called containerization, or to put all of the SMM code into a virtual machine so that its execution can be constrained. All right. So one of the things that's interesting